Hello, welcome everyone to this lecture on finite volume method. This is part of the numerical schemes description that we want to take you through one of the numerical schemes, which is finite volume method, which is typically employed in most of the commercial CFD software packages. What we would be expecting from you, having already gone through the lectures on fluid mechanics and heat transfer, and specifically the lecture on numerical methods, how these numerical methods are used to solve the PDEs, and surely you have gone through something on finite difference method, how a partial differential equation has been converted into linear algebraic equation using this finite method. What we are going to look today is on more specifically the finite volume method, which is also similar to finite difference method in that it converts the partial differential equations into linear algebraic equations. And I hope along with the assignment sheet that is provided, you should be able to answer some questions related with defining finite volume method and to approach to at least obtain a structured solution of a diffusion or a convection diffusion equation for a transport equation. Well, we'll go through the starting point for finite volume method, how a finite volume method works, what's the strategy. We'll see how it converts the partial differential equations to linear algebraic equations. Mind you, this is what all finite numerical schemes are intending to do, that they convert your given governing equation, which is usually in the partial differential form, that they are getting converted into linear algebraic equations. So we're going to see how finite volume method does this, and we're going to look at specifically two examples of transport equations, one without the diffusion term, one without the convection term, which means it has only the diffusion and the source term, and the other one having both convection diffusion term, but in both cases I'll be considering the steady state form of the transport equation. We'll start off with a one-dimensional equation and we'll move on to see how it can be applied for a two-dimensional or a three-dimensional case. So finite volume method, well, it is a numerical method. The most important part of finite volume method is that it is based on the integral form of your governing equations. So unlike the finite difference method, which requires the governing equations to be in the differential form, we are looking at the conservation equations of mass, momentum and energy, which are listed out here, that they should be in the integral form, as you can see it here. Well, the integral conservation law is actually implemented on the computational mesh or the grid that you provide to the solver, and what it considers is that it generates in some cases, or in some cases just takes the mesh to be the set of finite volumes, and it applies these conservation equations by applying the numerical scheme on these finite volumes. And the general scalar transport equation is familiar to us, so we're going to see how finite volume method can do this. So the first stage, in any case, we are familiar with this, that we need to generate a grid. We need to discretize our continuous geometry, which is in the computational language, like we have surfaces, we have volumes, we have surfaces which are defined according to some parameters. But when we come down to CFD, we want to discretize this geometry and we obtain something called mesh. What we try to do is we implement our governing equations on each of these finite volumes, and what we obtain ultimately is a set of linear algebraic equations. Now, why I'm saying linear, you would appreciate when you see the conservation equation, which is basically a nonlinear equation. Just have a look at the advection term here. You have the continuity, the 3 momentum and the energy equation. If it's a 2D problem as it is displayed here, it's x and y momentum. But what you can appreciate here is that this x and y momentum equations actually would have the velocity vector as well as the u or v term. Or in any other case, you will have the unknown phi along with the velocity field which may or may not be known. So that makes this advection term a non-linear term. And this is what we are going to see, how finite volume method takes care of it, that it applies linearization, that you ultimately obtain linear algebraic equations which have to be solved. So the finite volume method process works in this way, that we have the set of transport equations. In this case, it's a two-dimensional transport equation, which is steady state equation. So you have the advection term and you have the diffusion term along x and y direction, as well as the source term. Just to illustrate, I'm taking this simple example here. What we ultimately do is we convert it into the integral form. And when we convert it into the integral form, especially the advection and the diffusion term, when we apply it over the finite volumes, we actually get volume integrals, but we convert them further by applying something called the Gauss divergence theorem. I'm going to speak about it in a minute. We obtain the surface integrals. So we convert the volume integrals into surface integrals. And this surface integrals, our overall integral equation, when it is applied over finite volumes, so discrete geometry, in that case we obtain a discrete form of the equations. So you can see integration, which is a continuous representation, is converted into a discrete representation, that is summation form. As we saw in the finite difference method, we converted d by dx or dou by dou x. If it's a partial differential equation, we converted it into a difference equation. In the finite volume method, what we are doing is we are converting these integrals into summations, and that's the discretization. And as I mentioned to you, the advection term consists of the nonlinearity, and by an appropriate assumption, this equation is converted into a linear algebraic equation. A linear algebraic equation for a given cell, let's say we are discussing about cell P, we are applying this finite volume method for applying the conservation equation on this cell. What we obtain is a linear algebraic equation for a given unknown for which I'm solving. Let's say it's x momentum, y momentum, or any other transport equation. So that unknown is getting solved on this cell, and what we obtain is that unknown value being expressed in terms of the neighborhood terms, in terms of values preceding and succeeding this cell. So basically the neighborhood cells. So what you have, one unknown being expressed in terms of other unknowns around it. It's a one-dimensional case here. That's why what you see here is only a linear in one dimension. But in other cases, we might have a three-dimensional mesh. That's the usual geometry that we encounter. So you have the phi p, which is the unknown quantity at a given cell location P, being expressed in terms of the neighborhood terms. Now that's the linearized algebraic equation. And the other things that you see here, A, P, or B, these are all constant terms. These are things which are based on how we are converting it into linear algebraic equations. They depend upon what are the properties like density, or in this case the diffusion coefficient, or the source terms. These are what constitute these constants. Let's look at the finite volume method strategy in greater detail. So what we usually have, the transport equation, which is the governing principle, it is in the partial differential equation form. Mind you, we are ultimately trying to convert it into linear algebraic equation. So let's see the process. If we are applying the finite volume method, we first of all want our equations to be in the integral form. So that's anyway what we obtained from the Reynolds transport theorem, which is the basic principle or basic governing form of the equations. It's the integral form, it's the volume integral form. We apply something called the Gauss divergence theorem for the advection and the diffusion term, which is the second term on the left hand side of the transport equation and the first term on the right hand side of the transport equation, if you can remember what we usually see the general form of the transport equation. So by applying the Gauss divergence theorem, we are able to convert the volume integral of the advection term and the volume integral of the diffusion term into surface integrals. So they get applied over surfaces of the finite volume. So ultimately what we have is a mixture of volume and surface integrals. That's because still the first term on the left hand side, which is actually our transient term, and the last term on the right hand side, which is the source term, they still exist in the volume integral, although the diffusion and the convection term or the advection term have been converted into surface integrals. Further, we apply this on the discretized geometry. That's when the integrals get converted into summations. So you have the discretized form of the equations after applying your continuous form of the equations on the discretized geometry. And this is the stage when I am converting the discretized form using some approximation techniques. I'm going to speak about them later on in the lecture. By this approximations, we convert the discretized form, which is still representing the real life situation. We obtain something called the linear algebraic equations. Now, how valid these phase approximation techniques are, or these upwinding schemes are, which we are going to discuss later, how accurate they are is going to determine how quickly we obtain the solution to our problem. So this is just an overview of what we are ultimately trying to attain. We are trying to obtain the partial differential equations, converting them into linear algebraic equations. So this is our aim, to get to these linear algebraic equations. Once we have the linear algebraic equations, there are standard methods to solve them. That's at a later stage I'll be discussing when we discuss more in detail about the solver mathematics. So we'll see an application of finite volume method for the diffusion equation. This will be the first part of our discussion. So we have our equation, which is again, it's an ordinary differential equation. Actually, it's not a partial differential equation, but this is because it is being applied in a one-dimensional form. So you can imagine properties getting transported not by the velocity field, but it is just getting diffused, and maybe there's a source term inside. Now, typical example, a practical problem, is a 1D heat conduction in a rod, or if you can more specifically imagine, it's like a rod which has been insulated all around it so that the heat transfer is only occurring along the axial direction, that is one direction. Another example is if we have a very wide and tall wall, then the heat transfer from one side of the wall to the other side occurs only across the thickness. So that's a situation when we can imagine that your property is getting transported only in one dimension. When I gave the example of the rod, it's like heat is getting transported across the wall. There can be also mass diffusion, but I'll not discuss this. Let's keep the discussion simple. We are imagining heat is getting transported across a given object in one dimension. So that's a practical example. We'll treat nevertheless the quantity not as heat but rather as a general quantity phi, which has some boundary conditions. Now as you can see here, I'm specifying uh, a constant boundary condition, that is phi a and phi b. So the property phi has these bounds. This gives a unique solution to the problem inside the domain. It's not a parametric solution anymore. We'll obtain a unique solution. And additionally, what you can appreciate here, which I'll be discussing again when we discuss in detail about the solver boundary conditions, that I am specifying a given value of this property phi. I'm not specifying the gradients, I'm specifying the value. Now such a boundary condition is called a Dirichlet boundary condition. Some might like to pronounce it as Dirichlet boundary condition, but the Dirichlet boundary condition basically gives a unique value of the property being solved for, or the quantity being solved for, at the boundaries. So you get unique values. Unlike another boundary condition called the von Neumann boundary condition, or simply Neumann boundary condition, in which we specify not the value of the property but rather the gradient of the property. So that's a typical problem we are looking at. It's a 1D conduction or 1D diffusion problem which is steady state, and it's a one-dimensional problem. Therefore we'll try to obtain a solution for it. Mind you, we are trying to apply the finite volume method here. First step in any case for applying any numerical scheme is to generate the grid. So we'll try to obtain a grid for our problem. So what we'll end up in having is that we'll have a one dimension being divided into cells, being divided into volumes. Now one might ask the question, one may ask the question, why do we divide a one-dimensional rod into volumes? So how can we imagine this? Just imagine like there is a constant depth into the plane of the screen that you can see, as well as there is a unit height which is provided to this volume. So you can imagine it's like cubes which are progressing along this rod, along this line that you can see, and there are many such cells. But the transport of the property is only occurring along one direction. That's why it's a one-dimensional problem. So we generate a 1D grid, a one-dimensional grid, which basically means we just generate some bounds to this rod or the one-dimensional geometry that you have. So what you have is the geometry. We have the domain being discretized into control volumes. We obtain the nodal points. These are the cell centers in this case. As you can see here, we have a name P, which is the cell being considered, which is a volume being considered. There is a cell on the eastern side of it which has been termed capital E, and there is a cell on the western side of it which has been named as W. So we have a cell W and cell E bounding a cell P. At the boundaries between P and W cell, we have a western phase boundary which has been termed small w, and on the eastern side we have a small e representing the phase which is separating these two cells. So that's a description of the overall geometry which has been discretized. Let's move on. We'll try to now apply the finite volume method. Now, when we apply the finite volume method, what we have is these integral equations. So this is the volume integral equation which has been converted further into surface integral equations. And what we obtain after this is when we apply it over all the faces that bound the given cell. So what you will see is you will be applying this over the eastern phase, over the western phase, over the top phase, bottom phase, as well as if there is a phase into the thickness, into the plane of the screen that you can see, although we are not really interested in them because the north, the south, that is the top and bottom, and what is above this P on the screen and what is behind this cell P on the screen, it's not really sensible because we are having the transport of the property only along W and E faces. So therefore what we obtain is only this property being applied over the eastern phase and western phase. Now there is a step which is missing in between, which is the conversion of this volume integral into surface integrals. But if you can remember from the previous slides where we explained how the volume integral is converted for the diffusion and the advection term, in this case there is no advection term, so we have the volume integral for the diffusion term being converted into the surface integral form, and later on when we apply it over the given discretized geometry, what we obtain is the discretized form of the equation. So what you can see here is that still the source term, as you can appreciate here, source term has been classified as the source at the center of the cell multiplied by the volume of the control volume. So you have a proper discretized form of your governing equation. So you're converting the integral form into discretized form. So up to here we are okay with it. We have converted into the discretized form. Let's try to now get these values at the faces E and W. Basically we don't know the values at the face E and W except for the area of the phase and gamma, which is the diffusion coefficient, and we might know the value of source at discrete locations according to the function s which has been provided. But our aim now, or our challenge, is to express this d phi by dx at eastern phase and d phi by dx at the western phase. Just one comment here, that this minus sign comes into picture because there is a dot product of this differential of this gradient of phi with respect to the surface normal. So on the eastern phase the surface normal is going forward, as you can see here, that we have eastern phase. If I am inside the cell, I'll see that the surface normal will be going outward. On the western phase, on the other hand, the surface normal will be going outward, and which would mean against the direction of the positive x direction. That's why we have this minus sign associated with western phase term. So what we obtain ultimately is this discretized form of the equation. Now we'll see how we can now apply the appropriate assumptions and obtain the form which we require to have ultimately the linear algebraic equations. So we are trying to apply the discretization. So you can see here this d phi by dx on the eastern and western faces, we have to obtain them, and we are going to do some interpolation. So that's the approximations which are going to come up. So what we have is the d phi by dx on the eastern and western phase being expressed as a simple finite difference philosophy. So you have phi e minus phi p upon delta x. This is the spacing between the cell centers p and e. But you have also things at the eastern phase for gamma and a. Let's imagine that they are the same. It's not really varying. So in that case, you can simply take an average as well. So this is how this gamma w and gamma is e, that is on the eastern and western faces, are being represented in terms of the cell centroid values, because our aim is to get a linear algebraic equation in the form that you have all the unknown quantities phi expressed in terms of the finite volumes value, that is the value at the center of your finite volume. Additionally, we have the source term, which is S bar, which is representing the value inside the cell P, multiplied by the volume of the control volume being analyzed, and it is being expressed in terms of SU plus SP phi P. You'll appreciate this when we have a look at the convection diffusion form, but this is the usual convention which is followed, so I'm just following the same. We'll move ahead. And ultimately, when we apply this into the equation which we had earlier, what we obtain is a rearranged form in which we have um, these coefficients AP and phi P, AAP and AW and AE, as well as the source SU, and the unknown terms are still there, phi P, phi W and phi E. So what you can see here is that we have the unknown terms phi p, phi w and phi e in a linearized form. It's an algebraic equation. So you have the unknown quantity at cell P being expressed in terms of the neighborhood terms with some constants AW, AE and AP and SU, which have been tabulated here. This is just based on our application of the approximations which we have considered, and as you can see, one of the approximations is how we evaluate this d by dx, that is d by dx on the eastern phase and d by dx on the western phase, and that's how we obtain the form as you can see on the screen. So you have AW and AE and AP being expressed in a tabular form here. What you can appreciate here is that these coefficients depend upon the value of the diffusion coefficient on the faces, which of course we can express in terms of cell centroid values. Additionally, it is also dependent upon the area of the faces. So that's a characteristic of your cell. Additionally, also what you can see here is delta x WP and delta x PE. So this delta x represents the distance between the two cell centroids P and W or P and E, depending upon what you are trying to look at. And what you can appreciate here is this is where the grid information comes into picture. So the grid, the coarser it is or the finer it is, this is represented into the equation through these coefficients AW and AE and AP. So your grid is being accounted for in the discretization of the equations. So we have the equations, we apply the finite volume method, and on the discretized geometry we get unique values of these coefficients, which make these linear algebraic equations also unique. So ultimately, once we have the linear algebraic equation, the set of equations, we'll try to solve them.